My name is Thomas Jalabert. I'm a postdoctoral researcher in IMEP LAC in Grenoble, and I'm working on semi-conducting piezoelectric nanowires. And we use characterization techniques which are based on atomic force microscope. And today I will present one of these techniques, which is a piezo response force microscopy. So to begin with, just to remind some basic concepts of piezoelectricity. So piezoelectricity is an energy conversion phenomenon which occurs in non-central symmetric crystals. So here the atoms have different electronic affinities, so that when one applies a pressure, this results in an electrical dipole, and therefore it results in a macroscopic voltage at the terminals of the material. And this voltage depends on whether you pull or push on the sample. So we distinguish two effects. So the direct piezoelectric effect, where a force results in an electrical field, and there is also the converse effect, an electrical field results in a deformation. So because of these properties, piezoelectric materials are used in many applications. We can find them in printers, pickers, and other industries. And they use either the direct or converse effects. So one can find about mechanical sensors or energy harvesting. I will come back later on energy harvesting applications. And also because of the fact that we need quite large voltage to result in a relatively small deformation, piezoelectric materials are interesting in the industry to induce as actuators small displacements with high accuracy. So as a researcher, we don't only look for materials with the largest piezoelectric properties, but we also want to replace the toxic components, because one of piezoelectric material which is widely used is PZT, which is based on lead. So it's a toxic material, and it's an issue for medical applications. We also want to use non-critical materials, because so many metals may become critical materials in the near future, but I'm especially thinking about batteries, because we need many critical materials in batteries, and it is possible using the direct piezoelectric effect to, when it is possible, to use the mechanical energy from the environment in order to create an electrical current. So it's possible to get rid of the batteries by powering directly the devices with the environment. And it's also interesting in harsh environments where the maintenance, where it's difficult to maintain or replace the batteries. And among the piezoelectric materials we know, some of them are, such as zinc oxide, are also semi-conducting. So therefore, there are free charge carriers present in the material, which may actually screen the electrical potential which is created by the piezoelectricity. However, at the nanoscale, actually there are some depletion phenomenon which occurs near the surfaces. So these two effects, depletion and screening, competes. And therefore, this is a fundamental interest to study these effects at the nanoscale, and there is still room for optimization to optimize these semi-conducting piezoelectric materials. So we need actually nano characterization technique at the nanoscale. So that's why we use piezo response force microscopy, which is based on atomic force microscope. So to this outline our presentation, I will start by explaining what is piezo response force microscopy, and then I will show examples of characterization of thin films on nanowires. So you may know atomic force microscopy as a tool to probe the surface of a sample and to map the topography. And here we use actually conductive tips in order to apply an AC voltage between the tip and the sample. And because of the converse piezoelectric effects, this results in a deformation of the materials that we can measure by the AFM using a locking technique. And so we have a varying voltage, which is an AC voltage, and we have also piezo response, and the shape of this piezo response signals give information about the material, because given the crystal axis of the material, we can either have a piezo response signal which is in phase or out of phase with applied bias, and this therefore gives the information about the C-axis of a piezoelectric material, and also the amplitude of deformation divided by the applied voltage gives the piezoelectric coefficient d33. So piezo response force microscopy gives these two informations. So now, how could we characterize thin films? So it's possible to, because these thin films are flat, it's possible to use what we call the contact mode of the FM. So the tip is in contact with the sample and scans the surface of the sample. And therefore, we can record simultaneously the topography and the PFM amplitude and PFM phase of the material. So this is zinc oxide thin film. And here we have the same image. This is the side view, and here the top view. And we see some grains that we also recover on the topography we record with the FM. And that, what's interesting with the FM is that we can also measure at the same time the PFM properties. So this is the amplitude of deformation of the materials as a function of position, from which one can extract an average piezoelectric coefficient. And this is the phase of this signal as a function of position. And what is striking here is that we can, on this kind of material, on this kind of thin film, there are both polarities, zinc and oxygen polarities, which are present at the surface of the material. And therefore, this can lower the piezoelectric performances because the two polarities may compete. So for thin films, we have mixed polarities, and also one other thing I mentioned in the introduction is the depletion effects which occurs at the nanoscale, and because of the small surface to volume ratio in thin films, these depletion effects are less likely to occur. So that's why we are interested also in nanowires. So zinc oxide, these are same images, top view and side view of zinc oxide nanowires, which are about 3 micrometers long and 200 have a diameter of 200 nanometers. And so zinc nanowires are interesting because they are also mechanical properties which are interesting, such as high flexibility and high sensitivity to small forces, which is interesting to create some mechanical sensors. And also, it is possible to integrate them in nanocomposites, even if they are nanowires. So here is an example of vertically aligned nanowires embedded in between two electrodes. And at the microscopic scale, this looks like this. And it's possible to bend them or to apply a pressure on them in order to generate some electrical currents. It is what we call a vertically integrated nanogenerators. And if you are interested in the physics of these samples, I invite you to follow the presentation of Gustavo Ardila this afternoon, who will focus on these nanogenerators. And as far as I'm concerned, I will focus on the characterization technique, which is PFM. And this is complementary with the study of things. And yes, because of the large surface to volume ratio of these nanowires, the depletion mechanism are more likely to occur. So there is a comprehensive study and interesting physical phenomena arising in these samples. So how could we characterize nanowires by PFM? So by contrast with the thin films, it is not possible to use what we call the contact mode, because if so, during the scan, the tip may actually destroy the vertically aligned nanowires. So one solution would be to deposit an insulating matrix between the nanowires here in order to mechanically consolidate them. And if we also etch the above part of the nanowires, we recover a flat surface. So it's possible to use the contact mode. However, this requires some additional fabrication steps. So mechanically, the nanowires are clamped by the surrounding matrix. So this is an artifact for the measurements. So the solution we use is what we call the data cube mode. So we have a tip which is in contact with the nanowire so that we can measure the piezo response properties, and we retract it. We can move it and approaching again for changing the position of the tip instead of staying in contact. So we lift the tip between each pixel. So we lift, we measure, and we retract. And however, this requires more time than the contact mode technique. So when we need to find a compromise between the resolution and the time measurement, this is the drawback of this detection mode technique. And what is interesting with PFM actually is that we can record this the amplitude and the phase of the piezo response of the sample, but we can also at the same time measure the mechanical properties. So to illustrate this, I focus on what happened during the approach. So when the tip is far from the sample here, this is the force exerted by the tip on the sample, and this is the tip to sample distance. When the tip is far, there is no force. And when the tip is in contact with the sample, we apply a force. There is a repulsive force between the tip and the sample. Whereas when we retract the tip, because of van der Waals interactions, before lifting the sample, the tip exerts an attractive force on the sample, and this is what we call the adhesion force. So before lifting the sample, the tip sticks to the sample. And this adhesion force actually depends on the local properties of the sample. And this is what we can see here. This is the topography image of vertically aligned nanowires, and this is the adhesion force. And we see that the adhesion force is lower on the top surface of the nanowires, by contrast with when the tip is in between nanowires, because there is a larger contact surface. So this gives mechanical information about the sample, which is useful to analyze the piezo response, because what we're interested in is the piezo response on the surface of the nanowires only. So we discuss about this physics in this paper. And we actually when we approach the tip, we set a given set points, so that the tip is in contact with the sample, and during this time we measure the piezo response properties. And if we plot the average piezo response as a function of position, we have here the PFM amplitude map as a function of position, and we see that we have large spatial resolution, because we can see that here the piezo response is a bit larger on the edge of the nanowires. So this is interesting for characterizing the physics at the nanoscale. And here we have the PFM phase, and we see that we have an homogeneous phase as a function of position by contrast with thin films. So this is an interesting advantage for nanowires. And also the piezo response amplitude we measure is larger by contrast with thin films. So this is a second advantage of nanowires by contrast with thin films. And I also I recall that there are also larger mechanical properties which are more interesting. The only drawbacks to characterize is that it's a bit more challenging. So to conclude, I hope I convinced you that nanowires have better piezoelectric performances than thin films, and that we have what we call a PFM detection method, which is a technique which allows local characterization of piezoelectric performances at the nanoscale in this kind of nanostructures. And this PFM technique allows to better understand the physics and provide optimization guidelines for the nanocomposites, such as things vertically integrated nanogenerators. So with this, I would like to thank our technical staff and all our collaborators. And I also would like to thank you for your attention.